Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about Gaussian random vectors. The motivation is to describe the properties of what is arguably the most important parametric model for random vectors in multiple dimensions, which is the Gaussian parametric model. The prerequisites are linear algebra. We're going to use eigendecomposition of matrices, Gaussian random variables, multivariate continuous random variables, and marginal and conditional distributions. Let's begin by reminding ourselves what we know about Gaussian distributions and the Gaussian parametric model. The motivation to use this model is that sums of independent quantities are approximately Gaussian under mild conditions, as we will discuss in more depth later on when we talk about the central limit theorem. But for now, we're just going to accept the Gaussian density as a reasonable parametric model for certain quantities. This parametric model, this density, is parameterized by two parameters. The first one is the mean, and the second one is the standard deviation. The words mean and standard deviation, these terms, have meaning beyond the Gaussian parametric model, which we're also going to discuss in the future in the course. But for now, we're going to accept them as parameters. So what does the mean tell us? The mean tells us where the density is centered. If we shift the mean, the density shifts. And because of the exponential here, that's important to remind ourselves, because of the exponential here, we're going to have a fast decay away from the mean, because this exponential receives the square of a certain number, so positive values that are then multiplied by -1, and then this negative exponential is going to decay very fast away from the mean. We'll see a picture in a moment. Then there's this other parameter, sigma, and what sigma does is it controls how spread out the distribution is around its mean. Okay, so we know that it's going to decay eventually towards 0, but how long does it take to decay? Okay, how spread out is it? Let's take a look at a couple of examples in 1D. Here, mu is equal to 3, so the density is centered at 3, and it's not very wide, relatively speaking, because the standard deviation is 1. If we increase the standard deviation, it becomes fatter, it becomes more spread out, and now we have shifted the mean to -2, so it's centered at -2. And now we have made the standard deviation even larger, so that it's even more spread out, and it's centered at 0. So now we're going to introduce a multidimensional generalization of this density. And this is how it looks like. So we're talking about a vector x in d dimensions, and if a vector x has a Gaussian distribution in d dimensions, then it's going to have a density that looks like this. Okay? This density looks a bit scary when you look at it, but it's actually quite similar to the 1D case, because we have an exponential here. Okay, we have an exponential here, so we are going to have some decay as long as this number is positive, because we have this minus there. And that number is in fact going to be constrained to be positive. We'll see in a moment. We have two parameters to parameterize the density. One of them tells us where the density is centered. Okay, so this mu parameter is going to determine where the density is centered in this d-dimensional space. This is exactly the same like the mu parameter in one dimension. Now mu is going to be a vector because it's going to tell us where we are in this d-dimensional space. So it's a d-dimensional vector. Okay, and again, it determines where the distribution is centered. There's another parameter which is a bit trickier to understand, which is a generalization of the standard deviation parameter. Okay, this parameter is a matrix. Here we have its inverse, and here we have its determinant. But you know, this part here, don't worry too much about it because it's just a normalizing factor so that the density integrates to 1 in d dimensions. So you can essentially ignore it now for our explanation. Let's focus on this part here though. We have the covariance matrix here. Before we just had 1 over sigma squared, and that determined how spread out the density was. Well, it turns out that this covariance matrix parameter also determines how spread out this density is, but in multiple dimensions. So it gets a little bit trickier. We're going to go into details in a moment. But before, I need to tell you that there are some constraints on this parameter, which is that it has to be symmetric and it has to be positive definite. It has to be positive definite because, as I said, this whole quantity needs to be positive, so that when we multiply it by this minus 1, it becomes negative. A positive definite matrix is a matrix such that for any vector v, if we do v transpose AV, if A is positive definite, this is strictly positive. Okay, so like this we ensure that we're going to get a decay of the exponential away from mu if sigma and its inverse, so I should say that if a matrix is positive definite, then its inverse is also going to be positive definite. If this guy is positive definite, then this whole thing is going to be positive, and we're going to get a decay away from sigma because of the exponential. But how does, what's the shape of this decay? This is not completely obvious. In order to study how the density decays depending on sigma, we're going to study the contour surfaces of the density. What do I mean by contour densities? Contour surfaces. So we already saw when we were visualizing densities in 2D, we looked at the contour lines. So contour surfaces are the same thing, but in D dimensions. Let me erase this stuff so that we see this better. So we're going to consider points for which the density has a constant value. Okay, so this whole thing is going to be equal to some constant big C. And if we realize constant, of course, with respect to the point, right? So this is the point at which we're evaluating the density. We're looking for points that have the same density, which means that the whole density is equal to a constant. The only dependence of the density with respect to x is within here. So if this part here is constant, then the whole density is constant. So we're just going to focus on that. We also realize that the only thing that mu is doing is centering, it's shifting x basically, centering the distribution at mu. So we're going to take mu as 0, and then every conclusion that we take will hold, but we'll just have to translate the density to be centered at mu. Okay, so we're interested, because of that, we're going to set mu equals to 0. We're interested in points where this function here is equal to a certain constant, because that means that the density is constant. If I just show you an inverse of a covariance matrix, and I forgot to say, by the way, I'm saying covariance matrix all the time. This is this parameter that we're referring to. That's also another term that is going to have a meaning beyond the Gaussian parametric model. We're going to discuss it in more detail in a future video. For now, just accept it as a parameter that determines the shape of this Gaussian distribution in D dimensions. Okay, so now we want to study how this happens, how this parameter determines this shape. And if I just give you the value of the inverse and I show it to you, it's going to be very difficult for you to figure out how these curves look, how these surfaces, if we're in D dimensions, or these lines, these contour lines look if we're just in 2 dimensions. However, it's going to be much, much clearer if we use the eigendecomposition of the covariance matrix. So in order to study the shape of the contour surfaces, it's going to be super useful to consider the eigendecomposition of the covariance matrix. So it turns out, and this is a major result in linear algebra, which is not very easy to prove, but I encourage you to look at a linear algebra book for the proof. We're not going to cover it here. It turns out that any symmetric matrix is going to have an eigendecomposition of this form. So usually eigendecompositions, you have the eigenvectors, then some diagonal matrix of eigenvalues, and then the inverse of the eigenvectors. But for symmetric matrices, it turns out that the eigenvectors are all orthogonal. Okay, here it has the eigenvectors that are all orthogonal, which means that the inverse of the matrix of eigenvectors is just the transpose of that same matrix. Those are called orthogonal matrices, and they represent rotations. Okay, and this we'll refer to that in a moment. But the point is that this always holds as long as you have a symmetric matrix, and we are constraining the covariance matrix of the Gaussian random vector to be symmetric, so this happens. Very important, the eigenvalues are all real, and in the case of covariance matrices, we're constraining them to be all positive, so that the matrix is positive definite. If they weren't, then there would be a way of making this term here, let me remind you, so if all the eigenvalues are not positive, there would be a way of making this term here negative, and then the density is not going to have the shape that we want, which is decaying away from the center. So that's why we constrain all the eigenvalues to be positive. Okay, so let's go back here. We're trying to study the contour lines. We're going to try to see the effect of the covariance matrix, and for that we're going to use its eigendecomposition. Because it's symmetric, it's going to have an eigendecomposition where the eigenvectors are real and they're orthogonal. Okay, so let's see how we use this eigendecomposition. Okay, so we're interested in these contour surfaces. Now we say, okay, the covariance matrix has this eigendecomposition. You can check that if you can write the covariance matrix like that, you can write its inverse like this. Okay, you just take the inverse of this. This is the diagonal matrix that has the eigenvalues. Because the eigenvalues are strictly positive, because the matrix is positive definite, this matrix here is just going to have 1 over each eigenvalue on the diagonal. And you can check that if you multiply these two things together. I forgot to put an inverse here. You're going to get the identity. Okay, so because you have this, then this is the eigendecomposition of the inverse covariance matrix. And we're going to plug it in here. Once we plug it in there, we notice that essentially here what we're doing is we're multiplying on the left and on the right by a matrix vector y, which is equal to u transpose x. As I said, what is u transpose x? Basically, this is just u1 transpose x, u2 transpose x, down to ud transpose x. This is basically just the coordinates of the vector x in this basis of eigenvectors. Okay? I don't know if you can hear the motorcycle going crazy out of my window. I'm sorry if you do. Okay, so we have expressed this vector x in terms of this basis of eigenvectors. Geometrically, what are we doing? We're kind of rotating the axes so that they're aligned with the eigenvectors. And after that, okay, we're applying this diagonal matrix. Okay, so let me write this like this. Here we have that after applying the diagonal matrix, basically we have, this is the sum from 1 to d of the entries of this vector in the basis of eigenvectors lambda I. Okay, so again, these are the coefficients of x in this basis of eigenvectors, because you obtain it by just taking inner product with each of the eigenvectors. Okay, and if this is equal to a constant, then how does this curve look like? So let's imagine that all the eigenvalues are equal to 1. In that case, we would have the sum of I squared is equal to 1. Well, to some constant, right? To some constant. So just as an example, imagine that we are in 2 dimensions, and imagine that the constant, sorry for my handwriting, imagine that the constant is equal, let's say, to, again, 1. So what is this shape? This shape is just a circle, right? So in multiple dimensions, this thing is just a sphere. And what happens if we divide here by some positive constant alpha and another positive constant beta? What we're doing is we're distorting the circle in the direction of the axis to create an ellipse. Okay, you might have seen this before. This is just the equation for an ellipse where we're distorting it. In multiple dimensions, if we have some constant here, then what we're doing is, again, distorting this sphere in multiple dimensions to get an ellipsoid. So it turns out that the contour lines of the Gaussian random vector, of the density of the Gaussian random vector, are an ellipsoid that is stretched in the direction of the eigenvectors, okay? Because these are the coefficients in a basis of eigenvectors. So in a way, we have rotated the space to align the axis with the eigenvectors, and then we have distorted the sphere. So what we conclude is that the density of the Gaussian random vector decays away from mu, away from its center. In this case, the center is 0 because we have assumed that mu is 0. And the way it decays is in a way that makes its contour surfaces look like ellipsoids that are stretched to different extents in the direction of the different eigenvectors. How this ellipsoid is rotated is determined by the eigenvectors of the covariance matrix, and how it's stretched in each of those directions is determined by the eigenvalues of the covariance matrix. And that is precisely how the covariance matrix determines the shape of the density of a Gaussian random vector. Let's take a look at an example. Okay, so we have an ellipsoid where the axes are aligned with the eigenvectors, and how stretched the ellipsoid is in each direction is determined by the eigenvalues. Okay, so we have a matrix here. We're gonna again center ourselves at 0. We have this covariance matrix. We take the eigen decomposition. We have 2 eigenvalues, and now we see the eigenvectors, which are, if you realize, diagonal vectors. This means that the ellipse is going to be rotated, so that it's, along a diagonal, and the stretch along each of those diagonals is determined by the 2 eigenvectors. So we expect to see more stretch in this direction, which is the direction of the first eigenvector. And then we're like the contour lines are going to be given by this equation. We're taking the coefficient of x in the direction of this vector, the coefficient of x in the direction of this vector. We would have a sphere if these guys, or a circle rather, because we were in 2D. If these guys were 1, they're not 1, so it's going to be an ellipsoid that is stretched in the direction of these guys. So this is how the density actually looks like if you look at the density values, the density values in this direction. But let's look at the contour lines. The contour lines are exactly like we said. It's an ellipse that is spread in the direction of the eigenvectors, and we have more spread. In fact, like the spread here is square root of 0.8, whereas the spread here is just square root of 0.2. Okay, so now we understand the shape of the density of Gaussian random vectors. You might remember that if we had a Gaussian random variable with 0 mean and unit standard deviation, if we multiplied it by a certain constant, then what happened is that the standard deviation of the resulting random variable would be equal to that constant, and if we shifted it by another constant mu, then that would be the mean of the new random variable. And I forgot to say the most important part. This new random variable, when we do this affine transformation, is always going to be Gaussian. The way we showed this was by first computing the CDF. I'm not going to go through the details. You can go back to the other video and take a look at the details. We went through we derived the CDF, and then we differentiated the CDF and realized that we obtained a Gaussian density that had exactly that mean and that standard deviation. And you can do actually this for any Gaussian with any mean and standard deviation. If you multiply, then it remains Gaussian, but you're just changing its standard deviation. If you add a constant to it, you're just shifting its mean. So it turns out that this also happens for Gaussian random vectors. If we have a Gaussian random vector of dimension d with a certain mean and a certain covariance matrix, and we apply a linear transformation where we're multiplying by a, and we're shifting by some vector b, then the result is always going to be Gaussian. The mean is going to be multiplied by the same matrix, and there's going to be a constant, this constant added to it. And the covariance matrix is going to have this other matrix multiplied on both sides. We're going to see why this actually makes sense in a future video. For the purpose of this video, it's not too important. But the point is that if we do a linear transformation of the Gaussian matrix, of the Gaussian random vector, then essentially we're distorting this ellipsoid that is the density according to what we just saw, like these contour surfaces of the density, but they are going to remain ellipsoidal, and the new ellipsoid is going to be given by this covariance matrix instead. Okay. We're not going to prove this, but the proof would be very similar to the previous one. We would compute the joint CDF, and then we would differentiate it, and then we would realize that it's actually a Gaussian density, and it has this covariance matrix and this mean. There is a very important consequence about this fact that linear transformations of Gaussian random vectors are still Gaussian, and that's that the marginal distributions of subvectors of Gaussian random vectors are actually also Gaussian. So let's look at this example, excuse me, where without loss of generality, we're going to be interested in the first subvector of the Gaussian random vector. We want to know what the distribution of this guy is. So for that, it's going to be useful to actually, well, let's move forward for a moment. We realize that we can just extract this guy from the whole Gaussian random vector by applying a matrix that first has an identity. If this guy has dimension m, then this identity is going to be m times m. That extracts x, and then we don't care about y, so we fill in with zeros. Okay? So that's a linear transformation that maps the full Gaussian random vector to the subvector. Okay, so now we go back to our result that tells us that this subvector is going to be Gaussian because it's obtained as a linear transformation of a Gaussian random vector, and its mean and standard deviation are going to be given, okay, maybe I should have written it in more detail here, by a mu, where a is this, so that's the identity, these zeros, and then mu x, where these are the first m entries of mu, and then mu y, and this is just going to be equal to mu x. So the mean is equal to mu x. And if you remember, for the new standard deviation, it's going to be equal to a times the standard deviation of the random vector z times a transpose. So it's the identity, 0, and then this matrix, where this is the first m by m submatrix, and then this other vector again. And what happens here is that if you compute this out, essentially everything gets zeroed out except this guy. Okay, so the new covariance matrix is going to be just the corresponding submatrix of the covariance matrix of the full random vector. Here is a picture in 2D, because it's very difficult. I mean, yeah, I don't know how to show you pictures in higher dimensions. This is the density of the whole random vector. If we marginalize, if we integrate with respect to x, okay, so we integrate here to obtain the marginal with respect to y, we obtain a Gaussian. If we integrate with respect to y to obtain the marginal of x, boom, we get another Gaussian. And this will happen also in higher dimensions. Okay, no matter how we marginalize a Gaussian random vector, we're always going to get a marginal distribution that is Gaussian. Okay, so now we're going to discuss conditional distributions of Gaussian random vectors, and for this we're going to first take a look at a very specific situation in 2D, and then we're going to see that we're going to uncover a phenomenon that will also hold in more general 2D situations and also in higher dimensions. So let's consider a Gaussian random vector A and B, which have zero mean, we're centered at 0. You know, changing the mean is not too interesting. We're just going to be shifting around. So that's why we're just going to make it 0 mean, and we have this covariance matrix. So from our previous result, we can already figure out that if we just look at the marginal of A, it's going to be a Gaussian random variable with standard deviation 1. Okay, by our previous result. Same with B. It's going to be a Gaussian random variable with a standard deviation equal to 1. But now we are interested in what is the conditional of B given A. What is the relationship, if you want, between A and B? And we're going to see that that relationship is governed by these off-diagonal terms of the covariance matrix. It turns out that those off-diagonal terms, in this case, so that it's symmetric, they have to be the same. and so that the matrix is positive definite, they have to be between -1 and 1. You can check this by just computing the corresponding eigenvalues, and you're going to see that in order for them to be positive, this number has to be between -1 and 1. This number we're going to call the correlation coefficient. This is another term that we're going to see makes sense beyond Gaussian random vectors, but for now, again, we're just going to think about it as a parameter. And we're going to see that it governs the relationship between A and B. Okay, so in order to take a look at what the density, the joint density of A and B looks like, depending on this value of this parameter rho, we first need to derive the inverse. Okay, and so I looked up, to be honest, I looked up in Google what's the inverse of a 2x2 matrix, got the formula, here it is, you can check that it holds. And this is the inverse, okay? So now I plugged it in to the density. So in order to plug it in, just to be very clear, inside here what we have is -1/2, and then we have AB times the inverse, so 1/1 minus rho squared, 1 minus rho, 1, and then AB. So if you multiply this out, what ends up happening is that the cross terms, where like A ends up multiplied with B, are governed by a minus rho, okay? Or alternative, this guy is multiplied by this, actually by this, okay? So that's why this appears here. And otherwise, the square term is just multiplied by 1 because of this. The B square term is just multiplied by 1 because of this. You can try to compute this out on your own. The point is that we get this expression. And now let's take a closer look at this expression. Here, I'm going to give you a sneak preview of where we're going. I'm going to try to split this. Okay, so I know that this guy has to be equal to f of A, the marginal, times the conditional by the chain rule. Okay, I know that this has to be the case. And what I realize here is that I'm kind of almost there, right? Because I have this A. I know from the marginal that the marginal has standard deviation 1 because, linear transformations of Gaussians are Gaussian, and we saw the covariance matrix, so the marginal is going to have standard deviation 1. So I'm kind of almost there. And I need to somehow massage this thing so that I can split it into two terms that are both valid densities. And the trick to achieve that is to realize that this term here is almost B minus rho A. Sorry, my A's always look like E's. Okay, there you go. B minus rho A squared. Okay, I almost have this. This is equal to B squared minus 2 rho AB. So I have these two guys, but then this is plus rho squared A squared, which I don't have because there's no rho squared here. So in order to be able to plug this in, which is going to be super useful to achieve this, you'll see in a moment. This is, it's not that this is completely obvious. This is just a technique so that I end up with a valid density at the end. I'm kind of trying to show you where we're going so that hopefully it makes a little bit more sense. The technique is called completing the square because we want to complete the square. Anyways, in order to get that, I'm going to add and subtract rho squared A squared. If I do that, I get indeed this guy, but then I've subtracted rho squared A squared, so I have to plug that there. But this is awesome because now I can indeed separate this thing, into this part where there's going to be a cancellation here with 1 minus rho squared, and I'm going to get exactly exponential of minus A squared over 2, which is the marginal of A. I'm very happy. And I'm going to take a square root of 2 pi from here to get the corresponding normalizing constant. And on the other hand, I have this thing which is exponential of minus B minus rho A squared, which looks like a Gaussian. And indeed it is a Gaussian. And it's divided by 2 minus rho squared here, but that's okay because I have a square root of 1 minus rho squared here, and I can take a square root of 2 pi here. Okay, so what I mean is that I can split this into the product of exactly the marginal of A, okay, where I've taken this term and taken it out, and another term where I've taken this term out, which has to be the conditional, right? Because this guy is the marginal, and we can see that it's a marginal for two reasons. First, we know because of the formula for marginals of Gaussian random variables that the marginal is like that, so we know it. So now if we divide this guy by the marginal, we get the conditional. But also, we can also just figure out that this is a valid density with respect to B. It's just a Gaussian with a mean rho A and standard deviation, so mean rho A and standard deviation equals to 1 minus rho squared. You know, like it's a valid Gaussian density. In particular, it's going to integrate to 1. So if we integrate this whole thing with respect to B, we're going to actually get this guy, because this integrates to 1 with respect to B. So this is another way of proving that the marginal is Gaussian and that it looks precisely like that. Okay, so now you have two alternative proofs, and here we actually did prove this completely. So it turns out that the conditional of B given A is a Gaussian with mean rho A and standard deviation 1 minus rho squared, so completely determined by rho. So let's take a closer look. Okay, so here I'm just repeating what I wrote before. We have this Gaussian random vector AB with zero mean and this covariance matrix. We're asking what's the conditional distribution of B given that A has this fixed value, and it turns out that it's completely determined by rho. If rho is 0, the conditional mean is just equal to 0 and the standard deviation is equal to 1. So the conditional is exactly equal to the marginal, which means for any value of A, which means that the two random variables are independent. And this is not very surprising, because if you put a 0 here, then you have an identity matrix, which means that the contour lines, by the argument that we were talking about before, are just going to be circles. So when I slice the circle, we'll see in a moment what I mean by that, all the conditions are going to look the same. However, when rho is larger than 1, what happens is that the mean approaches A, the more rho approaches 1, and the standard deviation is decreased. So we get concentrated close to A. Let's take a look at a few pictures. This is the case where rho is equal to 0. And what happens here is that when we look at the conditional, so here we're looking at the conditional where A is equal to 1. These are the contour lines. The contour lines are as circles because of what I just said. You know, you have the identity matrix as a covariance. Now when I slice this, wherever I slice it, I get the same thing. I get a Gaussian centered at 0, which looks like the marginal. Okay, so the two random variables are actually independent. However, when we modify rho, this is modifying the eigenvalues of the covariance matrix so that the contour lines are going to be skewed. And so here you don't see it very much, but the density has turned. We'll see it more when rho becomes even higher. Here rho is only 0.5. And when I take the conditional, it's going to be moving towards A, because rho is equal to 0.5. Notice that if rho was equal to minus 0.5, it would move towards minus A. Okay, so again, the contour lines are skewed because we have changed the eigenvalues by changing rho. And now when we slice the joint PDF, we do get different Gaussians, and they're going to be closer to A. Okay, in fact, the mean is going to be at rho A, which is 0.5 in this case. The standard deviation is also smaller than the standard deviation of the Gaussian. This is going to become even clearer when rho is equal to 0.5. So we see it here, that it's starting to concentrate close to A. So then when we take the conditional, which is that slice, notice that it looks Gaussian, like all the others. It's starting to come closer to 1, okay? So it's starting to come closer to 1 here. It's easier to see in the contour plots. When we take this slice, it's starting to come closer, you know, where the slice is like the density obtained by slicing the joint has a mean that is going to be closer to A. In fact, here it's going to be at 0.9. And if we slice in general, now the conditional is really close, is centered to be really close to A, okay? Because this, the covariance matrix makes it so that the ellipse is very, very skewed. Okay, so here's the picture of the conditional when rho is equal to 0.9. So this correlation coefficient completely determines the relationship between A and B. If rho is close to 1, B is very, very close to A. So when we reveal A, the value of B is actually going to be concentrated very close to A. And again, this connects to some more general concepts that we will talk about in a future video. Okay, so it turns out that this fact that we just proved, that conditionals of Gaussians are Gaussian, holds in general. Here I'm going to parameterize the covariance matrix of a 2D Gaussian in terms of a parameter rho. This parameterization is completely equivalent to have written it like sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. So just by the entries, okay? So I can write it like this, I can write it like this, it doesn't really matter. The point of why I'm writing it like here is because any positive definite matrix we can write like this for a rho that is between -1 and 1. And the formula that we're going to obtain for the conditional is very clean. It's kind of close to what we proved when sigma was equal to 1, sigma A, sorry, was equal to 1, sigma B was equal to 1, and mu A and mu B were equal to 0. So this is just a generalization. And it would be proved in exactly the same way. You would write out the density, and then you would split it into a marginal and a conditional. And what you realize is that, well, first of all, the marginals have mean mu A and a standard deviation sigma A, okay, by our result on linear transformations of covariance matrices. Okay, just to clarify, here the covariance matrix of a 1-by-1 Gaussian random variable is just the square of the standard deviation. Now, when we look at the conditional distribution of B given a certain value for A, what we see is that if we center A, okay, and we add the, first we have to, we have the, let me go step by step. We have the mean of B. How is the B of me, the mean, I think I said the B of me. Anyways, let's move on. First, you have to add the mean of B, okay? How is it shifted? Well, in order to see how it's shifted, what you do is you center A, okay? So this is centering, let me use the same color at least. You center A, and then you divide A by its standard deviation. That gets multiplied by this correlation coefficient rho, and then scaled by the standard deviation of B, and that gives you how mu is shifted. Okay, so it depends on the normalized, this actually is usually called standardized, okay, this is called the standardized version of A. You center it, you divide by standard deviation, so the standardized version of A, you scale it by the standard deviation of B, and then you multiply by rho, and that tells you how to shift mu. So I know that this was a little bit complicated, but at the end, the point, what I really want to show you here is that if mu is 0, then this doesn't shift at all. So you still get independence. And mu actually determines to what extent B is going to move towards A when we condition on A. When we look at the standard deviation, luckily, it looks much simpler. Here, basically, it's still 1 minus rho squared. We don't have a square root because here we're looking at the square of the standard deviation. And so I could have put just square roots everywhere, and it's the same variance. So basically the variance is reduced by a factor of 1 minus rho squared. So you can see that rho really governs to what extent B is getting close to A. Also when you have arbitrary means and arbitrary standard deviations. And the proof would be exactly the same, but I wanted to make our lives a little bit easy, so that's why I set the standard deviations to 1 and the means to 0. It turns out that in higher dimensions, the same happens. So you have, if you have a vector C that has a subvector x and a subvector y, these are the corresponding subvectors of the mean. this is the corresponding covariance matrix where we've separated it so that this guy is the covariance matrix of the subvector x, this guy is the covariance matrix of the subvector y, and now the relationship between x and y is going to govern by going to be governed by these off diagonals, which was the essentially where the correlation coefficient was in the 2×2 case. The formula is a little bit more complicated. If we fix x to be equal to a certain constant, how does the mean of the mean of y move, mu y? How does that move? Well, it moves towards, again, some standardized version of x by something that is governed by the off-diagonal. So if the off-diagonal is 0, again, we get independence. And the variance, again, changes in a way that is, again, governed by the off-diagonals. If the off-diagonals are 0, again, we get independence. Okay, so we get a very, very similar situation in higher dimensions, although the formulas maybe are a little bit more difficult to read. Okay, so all this story is really nice. We have learned that Gaussian random vectors have ellipsoidal densities. If you look at the marginal of those densities, they're also Gaussian. If you slice those densities to get conditionals, they're also Gaussian. But what happens with real data? How do we fit a Gaussian parametric model with real data? Well, what we do is we maximize the log likelihood of the model, just like we saw for the Gaussian random variable. The log likelihood is basically under IID assumptions, so we assume that all the data points come from a Gaussian random vector with the same distribution and they're independent samples. Under that assumption, we just multiply the density n times if we have n data points, and we put a log, and that's just because otherwise the values are so small that we're going to be numerically unstable, and we just maximize it. So we have an exponential here, so if you remember what we did for the Gaussian random variable, it's very similar. We just split this into a sum of what is in here, and then we have to do minus this part. I've ignored some parts here because we're maximizing only over mu and sigma, so everything that doesn't depend on mu and sigma I can just throw away. And I end up with this expression where I have max of minus minus, so I can just do minimum of the sum, so you were just minimizing this expression. And now you would want to check that this has a single minimum, so this is convex with respect to mu and sigma. We're not going to do that because it gets a little bit complicated, but it's actually convex. You can believe me or go check a more advanced book on convex optimization. And now, once we have checked that, now we just set the partial derivatives with respect to mu to 0 and the partial derivatives with respect to the entries of sigma to 0. We're only going to do it for mu because sigma, it gets a bit complicated with the matrix manipulations. It's not super interesting. It's just complicated matrix algebra. We want to minimize again this with respect to mu and sigma. We're going to do it for mu. So if we take the partial derivatives with respect to mu of this term here, then basically that's the gradient of this term with respect to mu. The gradient of a vector, so you have a vector V transpose times a matrix times V. Okay, if you have a function like this, and you take the gradient with respect to V of this function, that's just equal to A. Okay? So again, you would check that by computing the partial derivatives. It's not too difficult. So if we take the gradient with respect to mu here, we're going to get sigma minus 1 and this sum of xi minus mu. This thing can only be equal to 0. So we want to set this equal to 0. This can only be equal to 0 if this is 0, because this is positive definite, so it means that it's a full rank matrix. Like this, we obtain that this has to be equal to 0, so we get that the sum from I equals 1 to n of the data points has to be equal to n times mu, because we're adding also mu n times. And we end up with the fact that the value for the parameter mu is just the average. The average of all the data points tells us where we want to center this ellipsoidal density, which makes some sense. We're going to talk more about this later on, but if you do exactly what I just did in terms of setting the gradient to 0 for the sigma parameter, you get this object, which is called the sample covariance matrix, because it approximates the covariance matrix. As I said, we're going to talk more about covariance matrices in a future video. For now, this is how you compute the maximum likelihood of this parameter that governs the shape of the Gaussian random, the density of a Gaussian random vector. Okay, so now let's look at some data. This is data from the US Army dataset that I found online, which contains the height and the weight of about 4,000 men in the US Army. Now we're going to first fit this thing with KD, with a non-parametric estimator of the density. And this is how the contour lines look. And now we're going to fit a Gaussian. And now realize that when we're fitting a Gaussian, we want to somehow fit contour lines that are ellipsoidal, where we account, we have a density that accounts for these data points as well as possible, and our degrees of freedom are choosing where the eigenvectors are aligned. Okay, so choosing how this axis is aligned, and then spreading out the ellipse in different directions to try to fit the data as well as possible. If we do this with maximum likelihood, this is what we get. Okay, and it's actually, pretty similar to the density that we have with KD. So these data are actually pretty well modeled as a Gaussian random vector. Okay, although there is a little bit of a shape here where, this is a bit kind of shifted in this direction. You cannot do that with an ellipse. The ellipse can only have axes that do like this. So you cannot account for this kind of shape that you see there. That you can just not account for with the Gaussian random vector assumption. Here we have height against foot length. And, again, the idea here would be that we fit a Gaussian parametric model, so we're trying to find an, ellipse contour lines that fit this data well. This is what KD gives us, and this is what a Gaussian fit gives us. It's very, very close. In this case, actually even more than in the case of height and weight, it looks like the Gaussian parametric model is a really good model for this data. And the reason, again, is because of the central limit theorem. Things that are kind of averages of many different points end up having a Gaussian form. All right, so what have we learned? We have defined the density of Gaussian random vectors. We have analyzed the contour surfaces of the density and found them to be ellipsoidal using, again, the composition of this parameter that was called a covariance matrix. We have shown you that the marginal and conditional distributions of Gaussian random vectors are Gaussian. And we have also shown you how to fit real data using the Gaussian parametric model via maximum likelihood. Thank you very much.